Assalamu alaikum viewers, and welcome to my channel once again. And in this video we are going to learn how to prove inequalities or inequations by means of mathematical induction. For this purpose, let's have a look to one example related to it. So here we go. So you see here, this is an inequality or inequation, I must say, and we have to prove it that whether this inequality is valid or not with the help of mathematical induction. And here they have assigned for us the range of our the value of n, and it is that this inequality is true for all n is greater than or equals to 2, and they are basically the integral value of n. So they are basically what you say. In other words, it is the natural numbers, all the natural numbers greater than or equals to 2, because once they are the integral numbers greater than or equals to 2, that means they are natural numbers. So with the help of mathematical induction, we have to prove whether this inequality is true or not for this range of numbers. Okay, so you know that in mathematical induction you follow 3 major steps. Okay, and out of which the first one is the basic one, in which you select the very first number of your of the set of your n. And here, regarding this so assigned range of numbers, the very first number of this set for the n is 2. Okay, so basically the set of n is this, and it's representing the numbers, integral numbers greater than or equals to 2. So they are basically this, okay, up to the infinity. So the very first number of this set of n is your 2. So we, in the basic step, what you do, that you substitute n equals to 2 in this inequation, and you check whether this greater than sign is preserved or not. Okay, so let's have a look that for our p of n is this inequation. Keep this in mind, and let's start the basic step. Two cube is 8, we know that, and there you go. So you see the p of n over here is true for n equals to 2. This is the basic step. We have just done that. Okay, this is the starting. We have broken the ice, and it is satisfied for the first value of this set. Okay, now in the second step, this is the first step, and in the second step is our hypothesis step. Okay, in hypothesis we just assume that this p of n is true for n equals to k. On that basis we are going to approach to the third step, that is we have to prove this p of n true for n equals to k plus 1 on the base of that hypothesis. That is, so you see, for as suppose p of n is true for n equals to k, that is, at the place of your n you just substitute your k here, and this is our hypothesis, that we have just assumed that for n equals to k this inequality is satisfied, it is true. Okay, on this basis we are going to approach to our third step. This is the final one, in which we have to work on this, on the concept that that p of n will be true for n equals to k plus 1 if it is true for n equals to k. So as it is true for n equals to k, so it should be true for n equals to k plus 1. Let's see now. Okay, so you see, actually let us do a little rough work here. Sorry, like if let us do a small rough work. Okay, so it's not the part of the fair, but just for the convenience I'm doing this. So you see, if I substitute n equals to k plus 1, I just need to bring a picture in front of me before solving the remaining work, that how the inequation is going to look like then I substitute n equals to k plus 1 in it. Okay, so once when I substitute n equals to k plus 1 in this inequality, it looks like this. Okay, wherever I was having my n, I just put my k plus 1 there. So that's how this thing looks like. Okay, so you see, I have to work on this hypothetical inequation of mine in such a way that I should get this form. If I get this form, then I'm going to say that yes, p of n is true for n equals to k plus 1 if it is true for n equals to k. Okay, so this is the rough format that I have just obtained. So you see how I'm going to get 2k plus 2. What should I what kind of adjustment I should do in this equation? Let us call this as star, okay, for convenience. So what should I adjust, or what operation, what kind of adjustment I'm going to do so that I should get 2k plus 2 on this left hand side? So simply the concept comes in my mind, the idea comes in mind that you should multiply 2 at both sides. So in that case, you should add power 1 and you're going to get 2k plus 2. So let's simply multiply 2 at both sides, because our objective is to get 2k plus 2 at the left hand side of this inequality. For that purpose, the only idea is that multiply 2 at both sides. Okay, that's a common sense. Those who learn in those who have knowledge about the indices, they can easily understand that. So multiply this star equation both sides with your 2. Okay, that's it. Okay, so you see here the power is 1, base are same, they are getting multiplied. So in that case, you simply add up the powers, and over here the power is 1 and over here the power is 2k plus 1. So you simply write like this. Okay, and that's how you get it. Alright, so now you see it is going to be 2k plus 2 greater than 4k plus 6. Okay, now you know, you have studied, you have just seen in the question that n is the value greater than equals to 2, all the integral values greater than equals to 2. So and here k is equals to n. So you see that's quite clear that k is greater than equals to 2. So if k is greater than equals to 2, it means twice of k is obviously greater than equals to 2. Okay, so you see, if I simply break this 4k with 2k plus 2k plus 6, okay, I'm doing all this stuff just in order to get this format. Okay, this format or this format, same thing, but my objective is to bring this form. For that purpose, I'm doing this all endeavor. So okay, so you see I've just broken 4k in this way, in 2k plus 2k form. So now you see this 2 times 2 power k plus 2 is greater than this whole thing. If I just replace this 2k with 1, because my objective is to get 1 over here, so then you see the power greater than this inequality will remain preserved, because 2k is greater than equals to 2. So if I just write a number smaller than 2k, obviously this greater than sign is going to remain preserved. So this is mathematically permissible. I mean, this inequality will remain unharmed, I must say, if I replace this 2k with 1. Okay, so that's it. Now my objective is to obtain here, I repeat, I need to bring this format. Okay, I need 3 here, I need 2 here. So you see, if this left hand side term is greater than this whole thing. So if I just replace this 6 with my 4, then this greater than sign will remain unaffected, okay, or unchanged. Okay, because I'm just writing the number greater than the 6, so definitely this sign will remain unaffected. Okay, so now let us break this 4 in this form. Let us organize these terms here, and this thing will remain. Okay, I've just written this 2 along with the 2k, and this 1 and 2 on addition give me 3. So now I'm having this type and now it's all obtained here. So let us give the final touch. Okay. So you see your P of n is true for n equals to k plus 1 if it is true for n equals to k. Okay, so according to your mathematical induction, your P of n is therefore true for all integral value of n greater than and equal to 2. So that's how you do. So you see, while dealing with inequality, your objective is to maintain this inequality sign, and on that basis, in order to preserving this inequality sign, you are applying the logics here, so that you are adjusting the numbers in such a way that this inequality sign should remain unchanged. Okay, and this format should remain preserved. So on that basis, you are just putting up the logics, and logics are something that become rapid, so arrive rapidly more you practice. Okay, so more you just select such kind of problems and you just exercise on them, so this skill is going to be more and more refined. That's all I can say. So let's see one more example related to this. So here you go, one more example related to your inequalities. Okay, so let us apply, and here the set of numbers for n are the integral values greater than or equals to 5. So they are basically these numbers here you go. So this is it, this is the set of numbers, and for all these set of numbers, this inequality should be proven true in the light of mathematical induction. So how we are going to do it, I repeat that we are going to apply here 3 major steps. One is the basic, that starts from the very first value of the set of your n. Okay, after that you just perform the hypothetical step, and then on the basis of that hypothesis you are going to perform the third step, which is the final hit on the nail. Okay, so let's see. The basic step says that for n equals to the number which is the very first element of this set of n, it is 5 here. So let us substitute n equals to 5, and it is 5 minus 1. The factorial of your 5, you can check it from your calculator. I'm sorry, it is 120, and that's it. And 3 power 4 is 81, so 120 is greater than 81. That's true. So you see your P of n is true for n equals to 5. Okay, we have just broken the ice. Now move ahead to the hypothesis, and we are going to assume that our P of n is true for n equals to k. That is, at the place of your n, you're going to put your k. So it looks like this. Okay, let it be your star equation. Now on the basis of this star, you're going to apply your third step. Okay, see, so you see your objective. Perform some rough work here, that what you should get after applying the logic on this star equation, what form you should get. So you see the rough work tells that if I substitute n equals to k plus 1 in this equation, in the question form, that I should get this. Okay, this is something that I should get. So you see what I should multiply at both sides, so that I should get k plus 1 factorial on my left hand side. You say simply multiply k plus 1 at both sides. In that case, this left hand side is going to be converted into k plus 1. Now maybe this concept sounds somewhat difficult to the new learners. You can understand this by picking some numbers. Like if I talk about my 3 factorial, you know that your 3 factorial is 3 multiplied by 2 multiplied by 1. Okay, so 3 plus 1 factorial is actually your 4 factorial. Alright, so 4 factorial is something with the product of your 4 and then 3 and 2 and then 1. So you see, this is something that your k plus 1 is. So if I multiply both sides by my 4, I'm getting my 4 factorial. So this thing is my 4 factorial. So if I multiply, assume that 3 is your k, and this is 4 is your 3 plus 1, that is k plus 1. So this thing is equal to your k plus 1 whole factorial. Alright, so that's what the thing is. So if you just multiply both sides by your k plus 1, and you can get k plus 1 factorial at the left hand side. So let us apply your step number 3. Okay, so I'm multiplying k plus 1 at both sides of my star equation. Okay, so this thing comes out to be your k plus 1 factorial, and this k minus 1, how I'm going to adjust this side in order to get my 3k plus 1. You know that your k is equals to n, and n is greater than or equals to 5, so it means that your k is greater than or equals to 5 over here. Okay, so this shows that if I just this number k is greater than or equals to 5. All right, so if I just replace my k with my number 2, okay, number 2, why I'm using number 2 in that case, I'm going to get my 3, so 3 power 1, when it is going to be adjusted with my 3 power k minus 1, I'm going to get my 3k. So that's why I'm using 2 here. Otherwise I was also able to put 3, 4 value as well at the place of my k in order to preserve this greater than sign, because presently we are in the process of mathematical induction. We haven't proven p of n true for all value of n greater than or equals to 5. We are presently in the process. So this thing is quite confirmed that if I select the value less than 5, then this greater than sign is obviously true. Okay, it is going to be unaffected, or it is going to be remain preserved. So that's the reason, in order to get 3k, 3 power k, I have just replaced my k with my 2. That is, if k is greater than or equals to 5, and this left hand side is greater than the right hand side, if I'm having k greater than or equals to 5. So if I simply replace my k at just at the right hand side, by my 2, then obviously this greater than sign will remain unaffected. So that makes sense. This becomes 3. Now once again apply the indices concept, that if two like bases are multiplied, you simply add up their powers. Here the power is 1. Okay. So let us arrange 3k minus 1. So this is the format. Like your P of n is true for n equals to k plus 1, if it is true for n equals to k. Okay, so according to thus, as it has been proven true, so according to mathematical induction, your given P of n is true for all n integral value of n greater than or equals to 5, and that's it. Okay, so you see, you are applying the adjustment in order to preserve this inequality and to prove this inequation. So on that basis, you are putting your logics here. Okay, so more you practice, more you get perfect. So try to attempt more and more questions related to inequalities in order to prove them mathematically with mathematical induction, and more you get perfect. Okay, that's all for today, and I appreciate if you subscribe to my channel, if you find this video helpful, and if the concept you feel that it is getting clear in your mind, and this video is contributing some role in it. So just try to put the hit on the like, and just subscribe to my channel, and try to share it with your friends and other learners. So thank you very much. I'll see you in future with some more helpful videos. Allah Hafiz.